effective nuclear charges. Effective nuclear charge, or ZEFF, effective Z or Z nuclear charge, is the positive charge felt by an electron or an outer electron around the nucleus of an atom. Now, different elements have different effective nuclear charges, therefore they have different atomic radii, they have different electronegativities and ionization energies. We're going to see some general trends in effective nuclear charge. We can see that it becomes bigger and bigger and bigger as we go to the right in the periodic table. This is because effective nuclear charge is the nuclear charge minus the shielding constant around of electrons on the outside of the atom, shielding by the inner electrons, or approximately, effective nuclear charge is about equal to the number of protons in the nucleus minus the number of inner or core electrons. So let's kind of draw this out. Take a look at hydrogen. It has one proton and one electron. So you can calculate ZEFF is, let's see, Z minus the number of inner or core electrons. And so there is Z, or the number of protons, of 1 for hydrogen, and the number of inner or core electrons between this one electron and the nucleus is 0. And so the effective nuclear charge for it is 1. Yet for helium, it's got 2 protons, yet still 0 core electrons. Its effective nuclear charge is 2. We can see that there is a different radius for hydrogen versus helium. Hydrogen is 37 picometers in radius, whereas helium is 31, significantly smaller. There's more effective pull of the nucleus for these electrons around helium than for hydrogen, because there are twice as many protons within the nucleus of helium than for hydrogen. Or go down another period in the periodic table, go from hydrogen to lithium. There is a tremendous increase in radius going from 37 picometers for hydrogen to lithium is 152 picometers in radius. This increase in radius is because instead of the electrons all being within just one shell around the nucleus, they're now filling 2 shells. As you go down in the periodic table, you fill in additional principal energy levels, or shells, and therefore increase the radius where those outer electrons are. Yet, as we go to the right in the periodic table, there will also be an increase in the number, in the effective nuclear charge. We can see this as we kind of fill in this table here. These elements, they all have the same number of core electrons. Lithium, it's got an electron configuration of 1s2, 2s1. For the electrons in principal energy level 2, there are 2 core electrons, 2 electrons in a lower principal energy level. Similarly for beryllium, it's 1s2, 2s2. For the electrons in principal energy level 2, there are 2 core electrons, the electrons in principal energy level 1. These elements all have 2 core electrons, yet they have different numbers of protons and nuclear charge. Lithium has 3 protons, beryllium has 4, 5, 6, 7, 8, 9, 10. Having increasing numbers of protons, yet the same shielding from those core electrons, there is a greater and greater and greater pull of the electrons on the outside towards the nucleus. And having greater pull, having greater effective nuclear charge, there's going to be a smaller and smaller and smaller radius as you go to the right in the periodic table. Yet, these might be our estimated effective nuclear charges, these whole numbers, 1, 2, 3, 4, 5, 6, 7, the actual effective nuclear charges are not exactly whole numbers. They range. Lithium is 1.28, beryllium is 1.91. We can see lithium is about 1 and beryllium is about 2. Yet, as we go further to the right, there's a smaller and smaller increase in effective nuclear charge because the inner or core electrons are not everything. There is still some repulsion of the electrons in the outer shell towards other electrons in the outer shell as well. So this equation is not a perfect descriptor of the status of effective nuclear charge. All right, so kind of summarizing what we just saw, and this is probably more pertinent to regular intro to chemistry high school students, we could see that as we go down in the periodic table, there is an increase in the radius because we start filling new principal energy levels. Whereas as we go to the right in the periodic table, where we have an increasing number of protons, but still the same number of inner or core electrons, we start having increasing effective nuclear charge as we go to the right. There's an increasing pull of the nucleus for those outer electrons, and therefore they get pulled in closer and closer to the nucleus as we go to the right, and therefore there's a decreasing radius. So kind of summarizing what we just saw, we have this postcard where right now we'll fill in radius, but we'll also fill this postcard in for electronegativity and ionization energy later. We can see that in the bottom left-hand corner of the periodic table, we have the largest radii, whereas in the top right-hand corner, we have the smallest radii. So bottom left-hand corner, large radii, top right corner, small radii for atoms. Now, we can see that there's some periodicity to the atomic radii of elements. We can see as we go from hydrogen to helium here, there's a small decrease in radius. And then as we go from lithium to neon, there is yet another decrease in radius. As we move to the right in the periodic table, going from lithium to neon, smaller and smaller radius. Then, as we hop into a new period, as we get to our next element, which is sodium, there is going to be a large increase in radius as we start filling principal energy level 3. Yet, as we go and continue in this period 3, there is yet another decrease in radius as we keep filling principal energy level 3. We're still filling the same principal energy level, yet there's more and more and more protons pulling towards those outer electrons, and therefore our smallest atomic radius is going to be argon in period 3. And then in period 4, again, we start with potassium at a very high atomic radius compared to the previous argon, because again we start filling a new principal energy level 4. And then we get to the D level where the rules kind of don't apply as much. And so kind of we more or less flatline whenever we get to the D block for a little while until we start falling again when we get to krypton. And then we can do rubidium, fall, D block more or less flatline, xenon, and then we have our cesium, D block more or less flatline, and then radon. Okay, so period 1, 2, 3, 4, 5, 6. Each period we see the same thing happening. Big up and then fall, big up and then fall. It's a periodic trend. This is kind of the basis of the word periodic table. Going down here, we can see that we're not always going to be talking about radii of atoms, but instead sometimes of ions. So we can see that sodium, let's say it reacts with chloride. Sodium loses an electron and chloride gains an electron. Sodium losing an electron is going to become quite smaller in radius. Instead of just filling out principal energy level 1, 2, and 3 as previous, it's now just going to be filling out principal energy level 1 and 2, being that it lost that electron in principal energy level 3. Filling out fewer principal energy levels and just having fewer electrons repelling each other, they're going to be more contracted in towards the nucleus, and therefore this cation, sodium cation, is going to be a lot smaller in radius than the original atom. Yes, losing electrons makes cations, and cations have smaller radii than the original atoms. It's the opposite, though, for anions. Chlorine gains an electron, and though it doesn't fill out a new principal energy level, it does have more electrons now than before, yet the same number of protons. Having more electrons which repel each other, those electrons are going to be spreading out more, and therefore your atomic radii, your anionic radii is going to be bigger than for the original atom. Yes, gaining electrons makes an atom turning into an anion, and anions have larger radii than the original atoms. Thanks for watching, guys.